Hi, welcome to tutorial number 3 of Introduction to Organic Chemistry. This one is on isomerism. So before we start, this might be quite a useful little graphic. So the idea of isomerism is branched into different ideas and different concepts. So we've got this overarching umbrella term called isomerism, and that splits. So we've got two different main types. We've got structural isomerism and stereoisomerism, and each of those is split into different types. So types of structural are chain isomers, position isomers, and functional group isomers. Under stereoisomerism, we've got geometric isomers and optical isomers. Now, I accept that's a load of words that don't really make any sense at the moment, so to illustrate what isomerism actually is and then to go through all of the different examples, first thing I want to do is look at a formula. So considering this formula, C5H12O, I would like to know what would that look like in displayed formula. So if you've got a moment, you could pause the video now, and in your notes, could you draw a displayed formula for C5H12O? So I'm going to assume that this is probably along the lines of what you've drawn. So we've got 5 carbon atoms in a row. We've got this alcohol group on the end, all your hydrogens in the correct places. So I'm assuming you've drawn pentanol. Or did you draw something like this? I would assume you probably didn't draw something like that. But if you look at both of these compounds and you count up what's in them, both of them contain 5 carbon atoms, 12 hydrogen atoms, and an oxygen atom. So this is the correct molecular formula for both of these compounds. So these two structures, these two compounds, are known as isomers of each other. So very simply, you can consider isomers to be different compounds that have the same molecular formula. So sometimes when you're looking at questions dealing with isomers and identifying different isomers, it can be quite puzzling because a lot of it is just to do with how many different ways can you arrange these atoms so that they're all bonding correctly, but now you've got a different compound than what you started with. Okay, so going back to our little kind of flow diagram here, this basically sets out the different things you can do with those atoms to produce a different compound. So in chain isomerism, for example, you change that carbon backbone, the chain of carbon atoms, you rearrange that. In positional isomers, you move a functional group around to a different point in the molecule. In functional group isomers, you actually change what that functional group is, but you keep the numbers and types of atoms the same. Now, in year 1, you're going to concentrate on structural isomerism to begin with, so we're going to go through chain, position, and functional group now. And you'll also deal with a little bit of stereoisomerism. We will also look at geometric isomerism, and that'll come at the end of this tutorial. Optical isomerism is saved for the start of year 2, so you don't need to worry about that one just yet. Okay, so first of all, just thinking about structural isomers, so this covers chain isomers, position isomers, and functional group isomers. You could be asked to define what that term structural isomers actually means. So structural isomers have the same molecular formula, but a different structural formula. So that might even be a 2-mark question to be able to say what's the same about them and what's different about them. So just as we saw previously with the C5H12O, those two compounds had the same molecular formula, C5H12O, but you could see once I'd drawn them out, if I was to write that as structural formula, they would then be different. So they are structural isomers. So on to the first type, we're going to look at chain isomers, so I'm just going to show you a couple of examples. Okay, so here are 3 different compounds. What's similar about them is that they all have the molecular formula C5H12. So they all have the same molecular formula, but looking at them you can see that they all have different structural formulae, so they are isomers. And the way that they have been changed, the way that they are different from each other, is that the chain of carbon atoms is different. So if we look for the main chain in each of these, we've got a chain of 5 here. This one, we've only got a chain of 4 with the other carbon coming off. This one, we've got a chain of 3 with 2 other carbons coming off. So we have branched the chain. So these second two are known as branched alkanes. So in terms of naming them, the first one is fairly straightforward. So we've got 5 carbons in a row, all single bonds. So this one would just be pentane. The second one, you've got 4 carbons in a row. So 4 carbons makes it the root name butane. We know it's ane because it's got all single bonds, but it does have an alkyl group sticking off the end, and it's 1 carbon in that alkyl group. So this is a methyl group. So we know that it must be methyl butane. And finally, you just need to say where that methyl is. So if we number these carbons to give them the lowest numbers in the final name, that methyl group comes off top, carbon number 2, so it's 2-methyl butane. Now this really is something to be aware of. If you're asked to draw isomers of C5H12, some people do tend to name them all based on pentane, but you need to remember that if you're branching a chain, now your longest chain of consecutive carbon atoms is shorter, so your root name will change to represent that. Okay, in the third example, you've got 3 carbons in a row, so we know that the root name is going to be based on propane. And you've got these 2 methyl groups coming off, so remember, because you've got 2 that are the same, we need to use a multiplier, so you've got dimethyl. And again, you just need to say on which carbon atom they are, so no matter which way you number this, they're both coming off carbon number 2. So it'd be 2, 2, dimethyl propane. And again, although it's a C5H12, it's now based on the root name propane because that's your longest carbon chain. Okay, your next type of structural isomerism is position isomers. So in position isomers, the functional group changes position along that carbon chain. So I'll show you some examples. Okay, so here we've got some compounds which are based on an alkane chain, but they've got a halogen atom attached. So I'll just highlight that for you. And to help us to name it, I've also highlighted your longest carbon chain. So if we look at the first one, we've got 4 carbons in a row, so we know that the root name is going to be butane. We've also got a bromine atom, so that's a prefix of bromo. And you need to say where it is. So if you number your carbons, 1, 2, 3, and 4, it's on carbon number 1. So it's 1-bromobutane. The second one has also got 4 carbons in a row, so it's also got a root name of butane. It's also got bromine atom, so it's got a prefix of bromo. But this time the position of that functional group, the position of that different atom, has moved along the chain. So if we number them 1, 2, 3, 4, this time it is on carbon number 2. So this one is 2-bromobutane, and it is a different compound from the previous one. Okay, and if you look at this third one, if you follow the same rules, what name would you come up with for that one? Would it be 3-bromobutane? Did you number your carbon atoms with the lowest numbers in mind? This one is not actually 3-bromobutane. This one, again, is 2-bromobutane, and that's something to bear in mind. If you look at these two compounds, people, when they're drawing out isomers, forget about numbering the carbon chain in the correct way to make sure that the lowest numbers end up in the name. So when you're listing loads and loads of different compounds that all are position isomers of each other, be careful you don't end up drawing 2 of the exact same compound again, because these last 2 are the same compound. If you were to take this one here, lift it up and flip it over, you would get that one there. It's exactly the same compound. And equally, if you were to move the bromine onto here, here, or here, it's not going to be 4-bromobutane, again, because you're numbering that way, it's going to be 1-bromobutane, and it would be exactly the same as that compound there. So that's position isomers with halogen atoms. I'll show you a couple of other examples of position isomers as well. So first of all, we're going to look at alcohols, and what happens if you move that functional group, the alcohol functional group, how you would name it differently. Okay, so here you've got 3 alcohols. I'll just highlight that alcohol functional group for you. Okay, and also your longest carbon chain so that you can name it. So it's there. Oh. There we go. So looking at this first one then, if you look at the alcohol group, we obviously know it's got 5 carbons in it, so it's going to be based on pentane, but it is an alcohol, so it needs a suffix. It's going to be pentanol. But you do need to say on which carbon atom this alcohol group is sitting. So if we number, so that your substituents are on the lowest number of carbon atoms, you can see that your alcohol group is on carbon number 1. So the way that you name alcohols when you need to specify position is like this: pentan 1-ol. So it's really important that you get your number 1 in the right place in the name. So you pretty much write the alkane name without the E. So it's pentane, take the E off to pentan, put your number in, and put the suffix ol on the end. So looking at the second one as well, this time we're not on carbon number 1, but we're on carbon number 2. So that one's going to be pentan 2-ol. And the third one down at the bottom, this time it's not on carbon 1, carbon 2, it's on carbon 3. And just to check, 1, 2, 3, doesn't matter which way you number it, that's going to be the name. So this one is pentan 3-ol. You do get a lot of students putting those numbers in random places in the word, so just make sure that you know where that number 1, 2 and 3 go in each of those names. So that's position isomers in alcohols. We're going to look at alkenes and then we'll move on to different type of isomers. Okay, so here's 2 alkenes. You can see that the primary carbon chain in both of them is 4 carbon atoms long, so the root name is going to be based on butane. But obviously because you've got a double bond in there, it's actually going to be butene. So both of these are butene, but they are different compounds because the double bond has changed position. So if I highlight that for you, you can see that on the first one the double bond is between carbons number 1 and 2, and on the second one it's between carbons 2 and 3. And the names of these compounds have to reflect that because they are different. So the way that it works with alkenes is, obviously your alkene, your double bond is between 2 different carbon atoms, so you choose the first one, the one with the lowest number. So for the first example, this double bond is between carbons 1 and 2, the lowest number is 1, so this one is not just butene, it's actually but1ene. So again, make sure that you know where that number goes. So the second one should be fairly straightforward now. That carbon-carbon double bond goes between carbons number 2 and 3, so that one is going to be but2ene. Okay, and your last type of structural isomerism is called functional group isomerism. And this is where the actual functional group itself changes. So these ones I would suggest that you learn in pairs. So there are certain functional groups where if you were to take those atoms apart and rearrange them, you can make another functional group. So I suggest the easiest way to learn this is to learn which functional groups can turn into each other. Okay, so first of all, for the molecular formula C5H10, I'm going to draw 2 different compounds that have different functional groups in them, but that do meet that molecular formula. Okay, so your first one is an alkene, and your second one is a cycloalkane. That is one pair that you can learn because one can turn into the other if you take those atoms apart and rearrange them. So both pentene, no matter where that double bond sits, and cyclopentane have 5 carbon atoms and 10 hydrogen atoms, so they are functional group isomers of each other. Okay, so for your next pair, we've got 2 compounds here, both with the molecular formula C3H6O, but with different structures, so these are isomers of each other. So the one on the left, these are a little bit less familiar than the previous ones. The one on the left is an aldehyde, and the one on the right is a ketone. So I'll highlight the functional groups for you. Okay, so in an aldehyde, you have this functional group on the end. Looks a little bit like a carboxylic acid, but it's missing this oxygen. So it's a carbon, double bonded to an oxygen and down to a hydrogen. That makes it an aldehyde. And a ketone is a double bonded oxygen that sits on one of the central carbons. So obviously if this was a longer chain, it could actually move position. It can never sit on the ends because then it would pretty much become an aldehyde. But it's on one of the central carbon atoms. So that's a ketone. So I'll name them for you as well. So this one on the left, the aldehyde, has got 3 carbon atoms in it, so it's prop, so it's propanol. And this one, 3 carbon atoms with a ketone, is propanone. So that's your next pair. Aldehydes and ketones are functional group isomers of each other. Okay, so your next 2 compounds both have the molecular formula C4H8O2, but they are very different compounds, as you can see. So the one on the left, you should recognise this one with this functional group as being a carboxylic acid with 4 carbon atoms, so this is butanoic acid. The one on the right, hopefully you remember this compound as well, or this functional group here, where you've got a carbon chain, what looks like it's going to be a carboxylic acid, but instead of the H, it goes on to a second carbon chain. This one is an ester. And to name it, we name this part first, the bit that's coming off the single bonded oxygen, that's ethyl, and the second part is ethanoate. So ethyl, representing this part of the compound, ethanoate, representing that part of the compound. So that's your third pair, carboxylic acid and ester, they are functional group isomers of each other. Okay, so just a summary, there are your three pairs of functional group isomers, alkenes with cycloalkanes, aldehydes with ketones, and carboxylic acids with esters. If you learn those, they should make your life a little bit easier when they give you, for example, an ester, and they say to you, can you draw a functional group isomer of this? You know that you're going to have to draw a carboxylic acid. Okay, so that is your introduction to chain isomerism, positional isomerism, and functional group isomerism. They're all types of structural isomerism, and structural isomers are compounds that have the same molecular formula but a different structural formula. Okay, so we're now going to look at stereoisomerism. We're just going to look at this one, geometric isomerism, and as I said, we'll leave that one for next year. So again, you might need to write a definition for stereoisomers, just like you might have needed to write one for structural isomers. So this is your definition. So stereoisomers have the same structural formula, but a different arrangement of atoms in space. So again, you can say what's the same about it, and this time it's important that you say structural formula and not molecular formula. So these are even more similar to each other than the structural isomers were, because they've actually got the same structure. And what's different? Different arrangement of atoms in space. Now you can see I've actually highlighted most of that definition. That's one I would just learn as it is, because if you word it slightly wrong, the examiner might think that you're thinking of structural isomers. You need to make it very clear that you know exactly what a stereoisomer is. So I'm going to show you some examples of that now. Okay, to understand geometric isomerism, you have to understand about rotation around the bonds. So if you look at this compound on the left, this is 1,2-dibromoethane. The one on the right is also 1,2-dibromoethane. They're actually the exact same compound, and that is because all of these single bonds, you can rotate about them. So you can twist around these bonds. And the bond that's important in changing this from this conformation to this conformation is this bond here. You can rotate around that, so you can take all of this part and you can rotate it around to get it to look like this. And that's happening all the time in these molecules. So these two are exactly the same compound, which is why when you're drawing things on carbon 1, carbon 2, it doesn't matter where you're pointing them, as long as they're coming off the right carbon atom when it's a single bond. Now, a problem arises when you've got a carbon-carbon double bond because the rotation is not free around those bonds. So I'll show you similar molecules, but with a double bond this time instead. Okay, so here's two new compounds. This is 1,2-dibromoethene, and this is 1,2-dibromoethene. So they've got the same name, they've got the same molecular formula, they've even got the same structural formula, because if you were to write this in structural, if you take each carbon in a row, you have CHBr, that represents this one, C, H and Br. Your next one is also C, H and Br. And if you were to write structural formula on this side, it's exactly the same, CHBr, CHBr. However, unlike the previous two examples, these two are not the same compound, because where you could have rotated around the single bond that's here, when you've got a double bond, there is limited rotation around there. You can't take this part of the compound and twist it round to get it to look like this. So this type of isomerism comes about due to a lack of rotation around a carbon-carbon double bond. Okay, so obviously we're going to have to name these differently so that we know that they are different compounds. Now I've put a little card up in the corner that will link to another video by Mackham Guy, who will show you using models how how these two compounds are actually different from each other. It goes a little bit in depth with orbitals and ideas of orbitals crossing over and the sharing of electrons, but it's useful to see how they are different using some models. So feel free to go and watch that video as well, and any other YouTube tutorials that you find that are linked to your specification could be useful as well. Okay, so the way that we name these compounds is we have two letters that go before the names. We use Z and E. Okay, these letters come from German, so Z is for zusammen, which means the same, and E for entgegen, which means opposite. So you don't need to worry about what they actually stand for. All you need to know is that Z means same and E means opposite. Now, if you look at these two compounds, it's quite easy to figure out which ones have things on the same side and which ones have things on opposite sides. So if you look across a compound, so we're going to pick the two bromine atoms here just to begin with. If you go across this compound from bromine across the double bond to bromine, you can see that those two bromines are on opposite sides of each other, so that is your E isomer. Okay, if you look at the other one, going from bromine to bromine, we go down across the double bond and up to the other bromine. These are on the same side, so these are the Z isomer. This molecule is the Z isomer. So you would name this compound exactly as you usually would, but then you would stick the Z or the E in front, like this. So they're both called 1,2-dibromoethene, but the one on the left, because those bromines are on opposite sides, this is E1,2-dibromoethene, and on the other one, they're on the same side, so that's Z1,2-dibromoethene. So now they've got different names, which indicates that they are actually different compounds. Now what you need to do is you need to be able to remember which one is E and which one is Z and what they actually mean. So there's a few different ways of doing it. I have a really weird way of doing it. So I think that this sort of shape looks a bit like a Z, so it's not Z, it's E. And I think this sort of shape looks a little bit like an E, so it's not, it's Z. So I remember them the opposite way round and remember that that's wrong. Lots of A-level students use Z is for the same side. So if you want to use that, that's what most seem to stick to. Or if you've got your own way, you need to make sure that you can remember that E means opposite sides or Z means same side. Now for something like 1,2-dibromoethene, that's nice and easy. You can clearly see which atom you're going from and to, because you've got two atoms that are the same on each carbon and two atoms that are the same on each carbon, and these two are different from each other. So that's nice and easy. Okay, sometimes it's not quite so simple, so we end up with an alkene that's actually got 4 different groups, and then you need to know, well, how do I know which group I'm going from and to? So I'll give you an example like that now. Okay, so this one, for example, has now got 4 different groups attached to those carbon atoms. So I'm going to try and name it first, and then we'll deal with the E and the Z afterwards. So it's got 2 carbon atoms in it, so we know it's going to be ethene. In terms of prefixes, we have got a fluoro, a bromo, and a chloro, so we need to be able to put those in alphabetical order. Okay, so in alphabetical order, they're bromo, chloro, and fluoro. And then we need to number these carbons so that we end up with the lowest numbers. So we would either end up with 1, 1, 2, or 1, 2, 2. So we'll go with 1, 1, 2 because it gives you lower numbers. So 1 bromo, 1 chloro, 2 fluoro, ethene. That's fine, but how do we know whether we're going from fluorine to bromine or fluorine to chlorine as we go across, or if we're going from hydrogen to chlorine or hydrogen to bromine, so that we can figure out whether it's E or Z? The way we get around that is we assign each of these substituents off that double bonded carbon group a priority, and these rules are called Karn-Ingold-Prelog priority rules. Okay, so I'm just going to run through those with you now. So first of all, we need to know what is the priority on the left-hand side of this double bond. So this group or this group, which one are we going to take as we look for which is E and which is Z? The way that we do that is we look at the first atom that is directly joined to this carbon atom. So if we go this way, it's a hydrogen. If we go this way, it's a fluorine. And the priority is assigned to the one with the highest atomic number. So hydrogen with an atomic number of 1 is obviously the lowest out of all of them. So fluorine has the higher atomic number. That one is going to be the priority. Okay, then we do the exact same on the other side. So we've got chlorine and we've got bromine directly attached to a carbon atom. So which one has the higher atomic number, highest number of protons? It is, of course, bromine. So your two priorities are fluorine and bromine. And now you can look, as you go from one priority group on the left over to another priority group on the right, are they on the same side or are they on opposite sides? So in this case, they're on the same side, or the same side. So it's going to be Z, 1 bromo, 1 chloro, 2 fluoro, ethene. So it's a Z isomer. So if it's unclear which atom you're going from and to when you go across the double bond to find out if it's E or Z, you look for the priority groups and they are the ones with the highest atomic number. Okay, so hopefully that's fairly straightforward, or at least it is when you've only got one atom in each of these 4 positions. Now obviously these could go off into big chains in different directions, so I'll briefly talk to you about that and then that'll be the end of this tutorial. Okay, so looking at this compound then, if we split it and we look at the left hand side first, so over here we need to choose whether this hydrogen atom on its own, that's the first thing that's directly attached to that carbon, whether that's the priority, or, be very careful now, you're looking at the atom that's directly attached. So you're ignoring this, ignore all the hydrogens, just the carbon atom. So compare those two, H or C, which one has the highest priority in terms of which one has the highest atomic number. So your priority on this side is that carbon atom, but you must ignore everything attached to that. So again, fairly straightforward. If you look on the right hand side, we've got to decide whether this carbon chain is the priority or whether this carbon chain is the priority. Okay, so if we go along this side, the atom that's directly attached to this carbon atom is a C. Okay, and the atom directly attached here is also a C. Now carbon and carbon both have the same atomic number, so they both have the same priority, so that doesn't help, that doesn't tell us which one is the priority group. So then you have to look at what is directly attached to these carbons. So we look at this one first, don't worry about that one because we've come from that direction. So in this direction we've got hydrogen, in that direction we've got hydrogen, in that direction we've got carbon. So CHH is what's attached to that one. Okay, that's for this carbon here. For this carbon, if you look at what's attached to it, in this direction we've got hydrogen, in that direction we've got hydrogen, and in that direction we've got hydrogen. So H, H, H. And you'll notice that I've written these in a particular order, so they're all the same, so that's fine. Here, I've put the C first when I've listed what's coming off of that carbon. So I've listed them with priority first, so highest atomic number. So now if you compare this list with this list, you can see that we're looking at C versus H. Which one has the higher priority? It's this one. That means that this group, this carbon atom, is your priority. So going from carbon atom to carbon atom through here, they're your two priority groups. Now, had we not got to a difference by the time we got to this carbon, you would just keep moving out further away, one atom at a time, and considering what is attached to each of those atoms and looking for a difference. So every time there's a tie, move one atom further out in both directions. Compare what's attached to it and see if there's a difference with atomic number, and when there is, you'll have a priority group and you're done. Now you can see in this one, in order to get from this carbon here across and up to this carbon here, you are going across opposite sides. Okay, so opposite sides means that it's an E isomer. So this one, I'm not going to worry about the full name, but it's the E isomer. Okay, and those rules that have helped us to determine which way we go are called the Carn-Ingle-Prelog rules, or the CIP rules, and it's all based on atomic number. Okay, so having watched that tutorial and the one before with the nomenclature, what I would expect you to be able to do now is switch between different types of formula and the names, so you can turn a name into a structural formula, structural into a skeletal formula, and so on, but also to be able to be very specific with those names if you've got some isomers. So being able to identify positions of functional groups using locants, the little numbers, identifying EZ isomers if you've got a double bond, knowing whether your molecule is the E form or the Z form. Obviously knowing which functional groups can be isomerized into other functional groups, so learn those pairs so that you know which ones turn into which. And understanding that your carbon chain, your long carbon chain, can change into shorter carbon chains with branches coming off, so you can turn a long chain alkane, straight chain alkane, into a branched alkane, and understand that then the name will change, the root name will become shorter, so you might go from something like pentane to methyl butane. So if you can make sure that you've got a set of tutorial notes to go with this tutorial, this one is really, really important, and then go on to your post-tutorial quiz and complete that for me, please. Thank you for listening.